I'm Richard Taylor, the CTO of Vector Photonics. Today I'm going to talk about the commercial journey of pixels and their pathway to high power. So before I start, I just want to speak about the photonics strength that exists in Scotland. So on the left is a map of Scotland with a heat map showing where photonics companies exist across Scotland. And you can see there's a lot of companies across the central belt. We ourselves are based at the West of Scotland Science Park, and on our site we have four companies, including ourselves. So GSS, M Squared, Coherent, and Vector Photonics, all on the same site. So this highlights the strength of the photonics community in Scotland, in Glasgow in particular. At Vector Photonics, we've got our world-class team of experience and expertise. This goes right throughout the team. And that's all enabled us to go on this on a journey of growth to date. So the story of Vector goes back to 2012 when myself, Dave Charles, and Richard Hogg were working on developing all semiconductor pixels back when we were working at the University of Sheffield. Initially, we worked on gallium arsenide-based devices. Then in 2019, we also did 50 nanometer pixels for telecoms applications. And that led to us being able to incorporate Vector Photonics in 2020. And since then, we've been able to secure £2.6 million in government grants, 1.7 million in equity investment. And that's allowed us to work towards commercialization. And we've grown throughout that to the point where we are almost 20 staff at the moment, and we plan to be 20 in the near future. One of the major advantages, one of the reasons why we work on photonic crystal lasers is their wavelength flexibility. So any laser you can make in a DFB or edge emitting laser, you can make into a pixel. And that means that we can operate any material system across the semiconductor spectrum. So we have in the past and still are working on 950 and 1040 nanometer lasers for metal printing. We also work on 13, 10, and 1550 nanometer devices, as well as 5 microns, so we can get complete material coverage. So we compare pixels to other light sources. So LEDs just give you spontaneous emission. If we look at edge emitting lasers, we have feedback and emission. And in those lasers, the feedback and the emission are in the same plane, and they're in the plane of the device. Next major breakthrough for lasers was obviously the VCSEL, where everything was rotated out of plane. So out of plane emission, out of plane feedback. But again, crucially, these two elements are in the same direction. With a pixel, we break that trend. And so we have in-plane feedback and out-of-plane emission. And that gives us the best of both worlds. So we can get the low packaging cost of a VCSEL, and we can get the high power of an edge emitting laser. So we're not limited by the power limitations or the wavelength limitations of a VCSEL. We're still a surface emitting laser. So the pixels have a unique property which allows them to be good for high speed and high power. So because of the in-plane nature of the feedback and the out-of-plane nature of the emission, you can scale devices to be large or small. As you scale devices up in size, the emission power increases. So this gives you routes to high power devices as you scale up in size, but also as you scale down in size, you can get devices with high speed. And that gives you one device platform that's suitable for small high speed chips and large high power chips. So just a conclusion of the different laser types. So pixels have surface emission, low cost. They've got flexible wavelengths and high power. VCSELs are surface emission, which gives you low cost, but they have limited power and limited wavelength reach. With edge emitting lasers and DFBs, if edge emission, which creates a packaging that's expensive, they do have the flexible wavelength and high power. So an additional advantage of making a large high power pixel is that as you increase device size, divergence comes down. This gives you routes to incredibly high brightnesses. So shown on the left are device size versus divergence for edge emitting lasers, VCSELs, and pixels. It shows that how we can increase device size to get a low divergent device. And the divergence measurement on the right shows the divergence of 0.4 degrees, which is for a device we actually make. And the in-plane feedback of pixels opens up a unique route towards power scaling. So because the light travels in plane in a device, you can couple this in-plane light between adjacent elements. In fact, that is what is shown on this, this array that we designed over here. So we have individual elements that each emit as an independent laser. Between these devices, we have a coupler region, which allows us to pump the region between the devices into transparency and couple the light between the two devices. So that means we can create a coherent array. So this experiment here shows what happens if we have two devices lasing. We overlay their image without making the coupler region transparent. Nothing particularly exciting is shown here. The exciting thing happens when we then pump the region into transparency here. We can see this interference pattern, which proves the devices are coherent across the entire device area, but also with each other. This coherence pattern indicates that we are able to make the devices coherent. This image on the right, what we show is that we can do that around a corner. So with 2x2 array, we take two diagonally separated devices, pump the regions between them, and get the same interference pattern, which shows that we can scale this in 2 dimensions. And this gives us a route to an n by n array, whereby we can keep scaling up until we reach the size of the wafer, and we can get potentially up to kilowatts of coherent power. We've been using this baseline technology in a funded Innovate project we've got called Bloodline. This is for 3D metal printing. So in conventional SLM systems, take a laser, you point it at a mirror, the mirror then scans the beam around, and that's how you do your metal printing. We intend to use this array-based system that we've developed to develop high single power, low divergence, so high brightness individual emitters, and create them into one of these arrays. What that will enable you to do is to write a large array all at once, and this will rapidly increase the speed of 3D printing and increase reduce your write time. Reducing the write time is the major contributor to reducing the cost of 3D printing. This is an international collaboration between Vector Photonics, the Compound Semiconductor Applications Catapult, the University of Glasgow, QD Laser in Japan, and it's funded by Innovate UK through the Eureka scheme. So this program we're working on will revolutionize the 3D metal printing with more than a 10-fold increase in power, which will give you solutions with no moving parts to give you rapid production. It's £1.5 million funded by Innovate UK, and this is to support the metal printing market, which is projected to be $10 billion by 2025. So just to summarize, so Vector Photonics all semiconductor pixel is going to in the future revolutionize 3D printing through the array system I've described. And this same technology allows kilowatts of coherent laser power at flexible wavelengths. And just to remind you, Vector Photonics is a company based in Scotland. We're leading this international from the UK, we're leading this international program. So last of all, I'd just like to thank the team that we've got working on this technology. So here's our team of engineers here who have been working on this project and the other projects we're working on moving forward. Thank you very much.